Part B of the TVM chapter deals strictly with annuities. We'll still be using the TVM keys on the calculator, but now the payment register will not be 0. An annuity is defined as a series of equal payments, inflows or outflows, that occur at regular intervals for a finite period. An ordinary annuity is one where the first payment occurs at the end of the period. This is the default in your calculator and in Excel. An annuity due is one in which the first payment occurs at the beginning of each period. A variation of an annuity is the perpetuity, equal payments, equal intervals, but the period is infinite. Preferred stock, which we cover in Chapter 9, is a perpetuity. These timelines show the difference between an ordinary annuity and an annuity due. Same number of payments, but with an annuity due, they all occur one period sooner. This drives a technique to solve for the value of an annuity due that we'll look at on upcoming slides. First, let's get valuing of perpetuity out of the way. Simple formula: payment divided by the required return. The formulas for the future value and present value of an ordinary annuity are shown on the slide. I have no expectations that you will actually use these formulas, but I'm showing them for a reason. These are the future value and present value formulas for annuities due. Note the difference between the two pairs of formulas. The value of an annuity due, future value or present value, equals the value of an comparable ordinary annuity times 1 plus the interest rate. This provides us with a solution technique. With an annuity, payment is no longer 0. Be very careful with the sign convention with a non-zero payment. Also, be very careful if you set your calculator to begin for an annuity due. Most problems are ordinary annuities, and you must remember to set your calculator back to end to avoid problems. Look at your calculator display. The upper right-hand corner is blank. Your calculator is set to end. To change to begin, press second begin. It's above the payment key. This is a toggle switch. To change to begin, press second and set. You'll see BGN appear in the upper right-hand corner. Press second and set again, and begin disappears. You're back to end. Press second and quit to set the displayed choice. Note, the calculator stays set to begin unless you change it back. This is great if you're continually dealing with annuities due. Not so good on a one-time basis, as you may forget to reset to end. We'll be using the TVM keys with the annuities, but the payment key is not 0. The sign convention is very important with payment. A wrong sign on present value or future value when payment is 0 only results in the wrong sign on the other. A wrong sign on payment can change the answer completely, not just the sign. Your calculator is capable of adjusting for value in an annuity due by changing the default settings. In Excel, we would still use the functions corresponding to the 5 TVM keys with one alteration. Type is 0 by default, which equates to end, and it can be left blank in Excel. To specify begin, type must be set to 1. We usually think of periods on the timeline as years, but they don't have to be. Period can mean months, weeks, whatever time frame is specified. It's important to remember that interest rate, time period, and payment period must match. Annual periods, years, means the interest rate must be an annual rate and any payment is an annual payment. Monthly periods means N is the number of months. The interest rate must be a monthly rate and the payment is a monthly payment. It's a sort of least common denominator situation. Do not forget the sign convention. This is important. These two problems look the same with one major difference. On the problem on the left, payment is a positive $20, implying that we will receive $20 every year for 5 years. Payment in the problem on the right is negative, implying that we add $20 to the account every year. Big difference. Everything else about the two problems is the same except the sign of the payment. Note that the answers don't just differ by sign, they're totally different. First, let's look at an example of solving for a future value of an ordinary annuity. 3-year annuity, 4% annual rate. You deposit $100 each year. Present value is 0 since the problem doesn't say you start with any money in your account. Payment is negative since you're depositing the $100 each year. Future value will be positive. This problem looks the same but is slightly different. 3-year ordinary annuity, 4% annual rate. The question is, how much do you need to deposit, negative, now to withdraw a positive $100 each year? N is 3, IY is 4. Payment is a positive $100. You're wanting to withdraw it. Future value is 0 because you want to draw the account down to 0 at the end of 3 years. Compute present value, $277.51. On the next 2 slides, we'll look at the same 2 examples we just covered for ordinary annuities, but analyze them as annuities do. First, look at the equation and solution in the red box. We're using the fact that an annuity due is equal to an ordinary annuity times 1 plus the discount rate, or changing the calculator setting to begin. Note that in the Excel example, type is set to 1 to indicate an annuity due. Solving the present value of an annuity due is handled in the same manner. Enter the ordinary annuity times 1 plus the discount rate, or set your calculator to begin and set type to 1. Let's take a quick look at the effective time on ordinary annuity values. Don't forget to set your calculator back to end if you changed it. On this slide, we're looking at a 5-year annuity, $100 each year, interest rate is 4%, present value $445.18. The 5-year annuity was $445.18. 10 years, $811.09. 25 years, $1562.21. Infinite, $2,500. So obviously, the longer you get the money in, the more it's worth today. Here's a real-world example of the power of compounding. A 20-year-old student wants to save $5 a day for her retirement. So every day she places $5 in a drawer. At the end of the year, she invests the accumulated savings, $1,825, in a brokerage account with an expected annual return of 8%. How much money will she have when she's 65 years old? This is the future value of an ordinary annuity problem. If she begins saving today, she'll have $705,373 at the end of 45 years. And there's your Excel. If a 40-year-old investor begins saving today and sticks to the plan, he or she will only have $133,418, $571,954 less. The moral, pays to start saving early. Suppose the 40-year-old wants to catch up with the 20-year-old. How much do they have to deposit each year to end up with the same amount? Almost $10,000. This ends our coverage of annuities. In the third part of Chapter 5, we finish our introduction to the time value of money.